means what? Okay, sample of AC current is like this. This is a sample of AC current that you're going to study in next subtopic and also chapter 4. Okay, once I finish the subtopic 3, it's a big relief for me because after that you can go very fast. It's easy after that. Yeah. Okay, so AC current. So for the AC current, okay, let's say for the first half cycle. Yeah. For the first half cycle, this one. Here, let's say positive, here negative. So current flow. Current flow. Let's identify the force. Where's the force acting? Where's the force acting? The force acting where?
Downward.
Downward. One, yeah? Okay. But now, if let's say, here, okay, hey, what happened? Okay, let's say for the negative half cycle, this is a negative half cycle. Current is already changed its direction, because over here positive, right? Okay, below is what? Below it is negative. So current change. So here negative, over here positive. Current flow. Okay, let's check the direction. Which direction? The force will be upward. So when the current keep on flow and change its direction, every half cycle, okay, every half cycle, what happened? Current change its direction. It will continue. Okay, all this you're going to study here. So what happened? This conductor will move down, up, up, and down. So it will move up and down because of directional current change every half cycle. So answer is up and down. Yeah. Never mind. Maybe you will confuse because of you don't know how AC current looks like and what is the what happened to the current that flow. Okay. Then we come to the next one. Is question number 14. This one normally they'll ask the force, but here they ask in the reverse way. Yeah? Figure shows the copper rod placed between the poles of magnet. What are the polarities of the magnet at H and K that will cause the copper rod to move in the direction shown? So here you can see what H. Here is K. And they already give you current. Okay, positive. Okay, you can see over here positive. Here negative. Okay, positive and negative. So current flow in this direction. Then they already give you the motion. Motion over here is what? Force. Okay, you have to try to place the Fleming's Latin rule in the correct direction. The third finger follow the current. Third finger follow the current. Current upward. And then the motion is to the right. Motion to the right. Where is the thumb? Points. Okay, wait. I draw this in on the whiteboard. Okay. So here we got a magnet. We don't know what pole is the magnet. Yeah. And then they say this conductor is moving to the right. Motion is to the right. And according to the terminals of the battery, current flow, okay, this is the direction of the current flow. So it's not perpendicular, right? Okay. So let's try using Fleming's third rule. Current outward. If you're observing from here, where is the current? Current is outward. Outward, motion, the force to the right. So you have to turn. Turn. Can see? Current outward, force to the right. Your second finger points what? Downward. Pointer shows what? Downward. Downward, that means here must be what? Here must be south or here must be north. Okay, normally we identify the force, but here what they did? They give the motion, they give the current, and then you have to identify the force. So answer is H will be north, K will be south. Okay, so that's all over here. Then we continue with the structured questions. Yeah, structured questions. Yeah. Okay. Electromagnetism. Wait, I remove the answers because yesterday I already discussed. Okay, so we continue with structured question. I think number 3 we already discussed. Is it already discussed this question last week? I think we already discussed this. Okay, we go for question number 4. Question number 4. Okay, diagram 6.1 shows the apparatus set up that used by a student to investigate the effect of magnetic field on a copper rod that is carrying an electric current. Carrying an electric current. In diagram 6.2, show the direction of the magnetic field before the switch is closed. Before the switch is closed. So it is a flat magnet. At the end over here, it must be what? Curved outward. It must be curved outward like this. Then center, make it straight. Not to south. Okay. Then when the switch is closed, the copper rod is observed to move along the copper electrodes. Draw the magnetic field that is formed from the combination of the permanent magnetic field, so permanent magnet field, and the magnetic field of the current flowing in the wire. That means here got magnetic field from the permanent magnet and also got magnetic field from the conductor that conducting current. When both fields combine, it will produce what? Resultant magnetic field. How it looks like? Okay, so simple. On top over here, south. Over here is what? North. So you're observing from here. Okay, you're observing from here, looking at the conductor. So current in or out? Current in or out? See over here, current, it is what? Outward, yeah? Outward. So that means we have to put what? Okay, current is outward. You see the arrow, current is outward. Okay, so then we have to put a dot. Okay, let's identify the direction of the force acting. Current out, not to south. Where's the force acting? Left or right? Left or right? Who want
Left.
to answer?
Yes, sir.
Yes? Left, huh? Left. Okay, if left, magnetic field will be moved to which side? Which side is it?
Right side got more.
Right side got more, yes. So make it more on the right side. This one must be practiced. Don't just read through from the books, yeah? So right side will be more. Okay, right side will be more. And then give a name for the magnetic field that is formed in B1. So what's the name for this? What is this? This field, call it what? Catapult field, yeah? Catapult. Okay, catapult field. Medan elastic. Okay, catapult field. Okay, in which direction does the copper rod move? Answer? To the left. To the left. Okay. State the name of the rules that relates the direction of the motion of the wire to the direction of the current and the magnetic field. So they ask you, name the rule. What rule is that? Yes?
Fleming's left-hand rule.
Fleming's left-hand rule. Yes, right with the correct spelling. Fleming's left-hand rule. Okay. Then we go for the next step. Step 1, yeah? 1, use of the rule that you have mentioned in C1 in the field of electromagnetism. So you write DC motor because the motor over here will use current and then it will be turned. So the turning effect needs what? The force. Okay, so we can identify the direction of force acting using what? Fleming's left-hand rule. So that means DC motor. DC motor. Okay, number 5, I leave it to you because answer is already given to you. Okay, and then number 5 completely, no need to go through. Okay, we come to question number 6. Yeah, question number 6. Diagram 8.1 shows a simple electromagnet used for lifting and releasing a small metal ball. In diagram 8.1, mark the direction of the current flows in the solenoid when the switch is on. Almost like this already test. They give the diagram, then they ask the students to draw the direction of the current. Okay, first you check the poles here. So terminals, positive, negative, current flow. So in front over here, you need to draw the direction of the current. First step, simple one. Then next one is name the magnetic pole at the end of the copy when the switch is on. So what pole is it at the P? How you're going to identify? How you're going to identify? What pole? We have to use what rule is that?
Right-hand grip rule.
Right. Yes, right hand grip rule because the soft iron core going to become what? Magnetized, yeah? Electromagnet. So right hand grip rule, grip correctly, curl the fingers, you'll get the P as what? What pole? You will get North Pole. Okay, you will get North Pole, yeah? Okay, you got the North Pole over here, no? You got North Pole here?
Yes.
Okay, so North Here's what? South, yeah? Okay, the next one is state the rule used to determine the poles of the magnetic field. Answer? How you are identifying the poles of the magnetic field? You are using what? Right and yes?
Nothing.
Yes, right and?
Right hand grip rule.
Right and grip rule. Okay. Finished? Okay. The next one is based on the solenoid in diagram 8.1, draw the magnetic field lines that is formed around the solenoid when the switch is on. In your diagram, show the direction of the magnetic field. So that means in this diagram, we are going to draw the magnetic field. Okay, magnetic field. So we draw this. Away from north towards the south. Okay, away from north and towards south. Okay. Finish. Okay. Now we move on to question number. Okay. Next question is here. This one. Okay. Based on table 8, state the suitable property to be chosen to build an electromagnet and state the reason for your choice. You want to make electromagnet. You want to use only one. Okay. The shape like N shape. Which one? I think I already taught you this in subtopic number 1. Yeah. If only one is not suitable, so we have to choose what? We have to choose the C shape or U or N shape, or we say what? Horseshoe. So here, the most suitable core is what? Core is soft iron. So answer there. Material used for the core, soft iron. Okay, reason why we choose soft iron? Because of easily magnetized and demagnetized. This point will be repeating again. Yeah, easily magnetized and demagnetized. Okay, easily magnetized and demagnetized. And then the reason, okay, the next one is the shape of the core. The shape is what? You can write N shape, or you can write U shape or C shape. Anything can. So here it looks like N, so you write N shape. So why it must be N shape? Okay, why it must be N shape? So that it can concentrate the magnetic field. So produce what? Stronger magnetic field. Okay, produce stronger magnetic field. Produce stronger magnetic field. Okay. Then question D here, this one electric bell. Also, they asked and explained before in terms of modification.
Sorry, sir, but the previous question, right, for the shape of the core, the one you said like N shape, right? The one, the thickness, does it affect the strength of the concentration of magnetic field?
The soft iron core.
No, because like one is tebal and one is like nipis.
Don't bother about that. We just go
Oh,
through the
okay.
shape now. Yeah, but you see the pairing from here to here. Pairing.
Yes, sir.
Okay. Okay. So the bell over here, yeah, in terms of bell, they can ask you the shape, C shape or N shape. Okay, number of turns of coil must be increased, produce a stronger electromagnet. And then we have to use a soft iron core, easily magnetized, demagnetized. Bell must be a large bell. Why? So that produce a louder sound. It can cause more air molecules to vibrate. When it's bigger, what happens? There's more air molecules inside, and it causes more air molecules to vibrate and produce a louder sound. Yeah. So this one I skip first, because we will discuss this when we come to pass this question again. Okay, we go for the second last question. Okay, diagram 5 demonstrates the force acting on the current carrying conductor in a magnetic field. When the switch is closed, what is observed? What is observed? Okay, positive, negative. Okay, so here, positive, negative. Okay, where is the current flow? Okay, let's draw the current. When the switch is closed, current flow. Over here, current is inward. In. Okay, in which direction this conductor will move? Who want to answer? Vikasni? Answer. Which direction it will move?
Upwards, sir.
Upward. How you know? What rule you are using?
Fleming's left-hand rule.
Fleming's left-hand rule. Yeah, so it will move upward. Force acting is upward. Correct. Thank you. Okay. So answer, you write upward. Okay, sorry. The copper wire move upward. Copper wire move upward. Okay. Then state the rule which can be used. Just now your friend already answer. Okay, this one make it number 1. This one number 2. Number 3. This one number 4. Okay. State the rules. Fleming's left-hand rule, or you can write right-hand slap rule. Only for the Fleming's left-hand rule, we can replace the right-hand slap rule. Some school teachers, they don't want to give marks. If let's say they didn't give you mark, okay, if they didn't give you mark, please, please correct it, okay? Please, okay, let's say if your teacher didn't give mark, please refer to textbook and then show. Because in the textbook, they already give that Fleming's certain rule can be replaced with right-hand slap rule. Is that already in your textbook? Okay. So next is if the direction of the current is reversed, what is the different observation can be made? So if the direction current reverse, what happened? Current now it's not downward. Current downward. So the conductor will move downward. So what different observation can be made? Copper wire move downward. Copper wire move downward. Okay, copper wire move downward. And then draw the pattern of the electromagnetic field that produce a motion of the copper wire as in A. In A. A is what? Moving upward. Correct? A is moving upward direction. So for that, let's draw. Okay, over here on the left hand side is south, right hand side is north. Okay, this one they ask you to draw the catapult field. Yeah? So current is in, so we have to put cross. Force acting is upward. Then the magnetic field from north. Always start from north, yeah? Then only you won't make mistake. Only one over here enough. Then don't forget to draw the arrow. Okay? Then, faster. How can the magnitude of the force be increased? Can be increased. Yeah? Can be increased. How? How we want to increase the force? So, simple, increase current. Or you can write use stronger magnet. Increase current or use stronger magnet. increase current or use stronger magnet. Okay. The last one is question number 8 before we continue the subtopic number 3. Figure 3 shows the two electromagnets P and Q. You can see like this in your textbook. It's there already, but slightly different. Yeah. So for each electromagnet, label the poles at the end, at the bottom of the course. So positive, negative. Okay, positive, negative. Okay. Then, okay, you see here, at this side, yeah, at this side, you can see over here, it's on the same side. When it's on the same side, confirm it will be like poles at the end. Yeah. So here, going to the front, over here, going to the back. Got different. That means confirm it will produce a strong electromagnet. Just observe this section also, you know already the answer. Which one is the most suitable? So, current, okay, which is a better electromagnet for lifting pieces of iron? Justify your choice. Answer. Okay, before that, let's check the poles at the P. Okay, so we use the right hand grip rule. What happened at this section? Here will be north, here will be south. Here also north, over here is what? Become south. That means like poles. If like poles, it will repel. That means the magnetic field is not being concentrated. But the second one, here north, over here south, use the right hand grip rule. Then here north, over here south. Then what happened to the magnetic field? Now the magnetic field will be what? Focused or concentrated. So produce what? Strong electromagnet. Okay, so we check the current, okay, in the solenoid, then identify the poles. Then we know already which one is a strong electromagnet. So answer, which is a better electromagnet? And justify your choice. Answer is Q. Why? Because there are opposite poles at the end of what? End of electromagnet or soft iron also can. End of course or coil, okay, or electromagnet. And then the magnetic field from the two coils combine to produce what? Strong resultant magnetic field or resultant field. Okay, the next page, I will give you the answer. You can check, except the C and D. Same like what we already discussed earlier. Okay, the last one, only this is the one that I want to discuss. Okay, the question you can study on your own. So, because it's not, we didn't discuss this in the exam. Also in the questions just now. So you look at the electromagnet A and also electromagnet B. In the electromagnet A, you see the battery, same. And here we are using iron block. Iron can be attracted by magnet. You see the number of turns of coil over here, less. Over here is what? More. So number of turns of coil over here, and here is what? This one more. When more, what happened? The electromagnet B become a strong electromagnet. When it is become strong electromagnet, what happened? The pulling force or the attractive force what? Greater. So let's say earlier is here, origin. Okay, origin is there. So when it is being pulled, okay, being pulled, it is being displaced a bit until here. But because of the electromagnet B, which consists of more number of turns of coil, it is become a strong electromagnet, and then it will pull the iron block with a greater force. So it will be what? Sorry, it will be displaced. It will be displaced more. You see, displaced more. Why? Because of the electromagnet B produce what? Strong force or greater force. Okay, why greater force? Because the number of turns of coil is increased, produce a strong electromagnet. Okay, so the rest you can go through on your own. Okay. Look at the question D now. Look at the question D. Oh, sorry, not this. Question D over here. Only this. What will be observed if the aluminum rod is replaced with steel? Okay, it's very simple. Steel and aluminum. Aluminum are lighter. Okay, if replaced with steel, what happens? Steel rod is what? High dense. High dense. If high dense is what? Heavy. Okay. And then next is what? Next is it has a very high resistance. If it has a high resistance, what happens? Current flow. Current flow become what? Lower. When current flow is lower, force acting is lower. Then the speed of the steel rod will decrease. Okay, speed of the steel rod will decrease. So answer is already given down there. You can check. But I already simplify. Important is in terms of density and also resistance. And what is the effect? Okay, on the motion of the conductor. It becomes bigger inertia. So the force is what? When the density is higher, is heavy, so moving on slowly. But and one more is resistance. Resistance of the copper rod. Steel rod is what? Higher than aluminum. Aluminum is very light. So when the resistance is higher, current that flowing in steel rod decrease and cause force acting become lower. Okay, so that's all. The rest you can go through on your own. Okay, electromagnetic induction. Okay, electromagnetic induction. So what is the mean by electromagnetic induction? Okay, induction, some sort like we say production, produce. Okay, so electromagnetic induction means is a process. It is a process of producing current. When? How the current is produced? So electromagnetic induction definition is process of setting up of current or EMF. Process of setting up of EMF Process of setting up of Darshini, what's the problem? Darshini, what's the problem? You exit and then joining back. Why? Internet slow?
Accidentally exit, sir.
Accidentally. Okay. Okay. Process of setting up a VMA or current. When a conductor or coil. You can write any one of this. Let a conductor or coil experience change of magnetic flux. A process of setting up of EMF or current when a conductor experience change of magnetic flux. So when we say experience over here means cut, yeah, cut. It refers to cut. Okay, let's say if I take a piece of paper. Okay, if I take a piece of paper or book, okay, let's say, but tell this, what you can feel? Can you feel the air? Yes, we can feel the flow of air. But can you see the air? No. So then we can feel there's a air movement. There's an air movement. But here, the conductor is going to experience here, there will be, there is a cutting of magnetic flux or magnetic field. So what is the magnetic flux? So let's say this is a north pole, or here is a south pole, and the shape of the magnet is not suitable. You know already. You must know the correction. I already explained to you before. You can apply it here again. And then the magnetic field is what? Not uniform. Yeah? It's almost uniform, but not uniform. So north to south. And then this is the one that we call it as magnetic field or magnetic flux. Okay, this one we call it as magnetic field or magnetic flux. Okay, magnetic field or magnetic flux. Okay. Later you want to screenshot can. Okay, now on it, you want to draw. Good. Okay, let's say here is the North Pole and over here is the South Pole. And then in between there is a magnetic field. Okay, in between there is a magnetic field, but we can't see the magnetic field. We can't see the magnetic field. But let's say if in between you place a conductor. Okay, let's say I place a aluminium rod, very light, or copper wire. Yeah. So if I place in between. Okay, it is in between. There's a magnetic field, so this magnetic field. So I place a conductor inside. Yeah, inside. And then this conductor I connect to centered zero galvanometer. Okay, centered zero galvanometer. Okay. Normally in school, the galvanometer that you are using is very sensitive. It can detect a small current. But when I asked the salesman to bring the galvanometer for me, he bring this galvanometer. This is a galvanometer, but it's less sensitive. Like what you're using in school is more sensitive. But this one, less sensitive. So you look at the pointer. This is a galvanometer. And then you see the pointer shows up 0. The 0 mark is at the middle. So left hand side negative, right hand side is what? Positive. Galvanometer. Okay. So it can deflect left or right. Later I will show you some activity. Centered zero galvanometer. Okay. And this conductor, one of the terminal I connect to here, and one more terminal I connect to the other side. Okay. Now, if this conductor it is being moved. Okay, if this conductor it is being moved upward. Okay, let's say if I move it upward. That what I did? I applied force on it. But in between there's a magnetic field. Not to solve like this. There's the magnetic field, but we can't see. Okay, magnetic field not to solve. Okay, magnetic field not to solve. Now the conductor is inside. When the conductor is being moved upward, is it cutting magnetic flux? Inside, it moves upward. Upward. Is it cutting magnetic flux? Yes, it's cutting. Right? It is cutting the magnetic flux. So once the conductor is moving in the direction of F given, so what happens? It will cut the magnetic flux. When cut the magnetic flux, but we can't see the magnetic field, but it will experience change of magnetic flux. I mean, it is cutting the magnetic flux. So what happens? Current is induced. Current induced. So I say what? Induced. So something like is produced. Okay, but don't use the word produce. Induced. So the induced current we can identify using Fleming's right hand rule. Okay, we have to use Fleming's right hand rule. Okay, what for we are using Fleming's right hand rule? So actually we are using Fleming's right hand rule to identify, direction of the induced current flow. Okay, so we use this rule for what? To identify direction of induced direction of induced current. But before this, Fleming's Latin rule left hand rule, what I give you? F B I, correct? FBI. Force, magnetic field. B for magnetic field, I is your current. FBI. Federal Bureau of Investigation, FBI. Okay, but don't write Federal Bureau of Investigation wrong. Yeah. So now we come to the right hand side, right hand. So same here force FBI, but now you write reverse FBI reverse, but still the thumb is force. Okay, so we write F B I. Okay, Kevin, off your mic. Kevin, off your mic. Mute. Thank you. Okay, so you can see over here force, magnetic field, and current. FBI. And then same like before, left hand, right hand, E triggers. First fire 90 degree. And then third must be perpendicular. So each fingers over here must be perpendicular, same like left hand. Same. So in this case, before this Fleming's second rule, what we did? We use the Fleming's second rule to identify the direction of the current. We are identifying the current. Now we are looking. Okay, sorry. In the Fleming's second rule, we are identifying the direction of force, in which direction the conductor will move. But here, the conductor, we are the one going to move the conductor, right? Moving the conductor. So what happened? We already know the force. We already know the magnetic field. We are looking for the current, induced current flow in which direction. So have a look, right hand, force upward. Your thumb must be upward. Wait, I need to check. Okay. Force upward to the south. To the south. Can see clear. And then the third figure, where it goes? Can see inward. Correct? Inward. In. So current flowing inward. This is the direction of the current. I repeat, force acting is upward. Upward. Magnetic field to the south. See, the third finger goes inward. Yeah, inward. So what happened? Galvanometer, pointer of the galvanometer deflect to the right. Okay, it is deflect to the right. Okay, it is deflecting to the right. Okay, it is clear. Yeah? It is clear because I can see what you can see over there. I can see clear. The way I place over here, you place it. I teach us what. Some of you at the back cannot see, but here can see clearly. Force upward, not to south. Third finger goes inward. So current in. So when you come to here, it is deflecting to the right. Okay, now I change the color. If let's say this conductor, it is being moved downward. Okay, I change color. It's the second case. I want to redraw again one more diagram. Yeah. Okay. So if the conductor is being moved downward, okay, let's check using right hand, force downward, magnetic field, the third finger over here, magnetic field to the south. You can see force downward, magnetic field to the south, and then this finger. Can see, right? This finger here, it is what? Outward. It is outward. Force downward, magnetic field to the south, and then the third finger. It is outward. So if outward, this is the direction of the current flow. Current. So when current flow in this direction, what happened? The pointer of the galvanometer will deflect to the left. Okay, it will deflect to the left. Okay, finish. Okay, finish. I'm going to erase this with the small changes. You want to screenshot, can. Then later you can redraw. Okay. Now, okay, so next one is we want to check when the current induced and when no current induced. Yeah? Okay, so just now I place a copper rod in between copper rod, and then we connect to the galvanometer. Okay. Now we are going to move this copper rod. Okay, first in the direction, let's say P, direction P. Okay, then next one is in the direction Q, and then in the direction R, S. Okay, we go through this purpose. All of you listen. P, Q, R, S. Here got magnetic field. The conductor is inside. Okay. If the conductor will move upward, is it cutting magnetic flux? Yes. It will cut the magnetic flux. That means it will experience change of magnetic flux. Yes, cutting. If the conductor is moving downward, is it cutting magnetic flux? Yes. Yes, yeah, it's moving downward. Yes, it's cutting magnetic flux. That means what happened? Current induced. Current induced if the conductor moving upward or moving downward because it cuts the magnetic flux. Okay, but now R and S. Here got magnetic field parallel. If the conductor is at the center, it is moving parallel to this. Is it current induced? No. If moving in the direction of R, in the direction of S inward, what happened? No current induced. Why? Because the conductor moved parallel to the magnetic field. So that means if you're moving in the direction of R and also in the direction of S, no current induced. And one more is T U. Okay? Magnetic field, if moving upward, have magnetic flux. Moving downward, yes, it's cutting magnetic flux. But moving inward, outward, no magnetic flux is being cut. But okay, one more is inside and also outward. In and out. Is it cutting magnetic flux? No. No. So that means if the conductor is moved out, and in, no current induced. Is not experience any change of magnetic flux. So conclusion over here is current induced in the conductor move in direction, P and Q. If you move in direction P or Q, what happens? Current induced. Okay, current induced. Okay, if you are moving in the direction P and Q, current induced. Okay, next one is no current induced if the conductor move in direction. No current induced if the conductor move in direction. That is what? R and S, they mean parallel. If R and S, no current induced. Yeah? So R and S, no current induced. Okay, and then one more is what? U and T. Okay, U and T. No current induced because it is not cutting magnetic flux. Once cut, yes, current is what? Induced. Okay, if cut magnetic flux, current induced. Okay. Okay, the next one is the magnitude of the current induced in a straight wire, in this wire. The magnitude. How to make the current induced become greater, more current induced. So what are the factors that affect magnitude of current induced in a straight wire? In a straight wire. I'm talking about one wire. Okay, so the next one is magnitude of current induced in a straight wire depends on magnitude of current induced in a straight wire depends on number one, speed. Number one, speed. How fast you are going to move. Wait, there's a law for this. Yeah, there's a law. Okay, speed. And then number 2 is strength of magnet. Strength of magnet. That means if we are using powerful magnet or strong magnet, what happens? It will produce what? Or it will induce more current. Don't worry, after we finish off this subtopic, it will back to normal, easy. Okay? Because after this subtopic will be transformer. After transformer, generation, transmission of electricity. Okay, so speed and strength of magnet. I mean the number of refers to number of magnetic fields. So if you are using strong magnet, the number of magnetic fields will be more, so more the current induced. So this one explained by a law. Explained by a law. Okay, later we go through that law. So here what we go through is the current induced in a straight wire. Current induced in a straight wire. How you're going to identify? How you're going to identify? Use what? Use Fleming's right hand rule. Use Fleming's right hand rule to identify the current in the direction of induced current in a straight wire. But now we are going to go through the next one is in a solenoid. You can screen this and then later you have to copy also, okay? Because I got another around 15 minutes plus. Okay, just now you saw, right? Current process of setting up a VMF when a conductor or coil experience change of many parts. So here we go through a conductor, but now how about the coil or solenoid? Yeah. Okay, I don't want to come out with so many turns of coil, just a few turns of coil. Okay, so here you can see solenoid. This is what you call solenoid. Okay, for empty space, right? Empty space. Okay, in between, follow. Okay, a lot of turns of coil, but here only 3 turns of coil, so that's easy for you to draw. And then let's say in front of it, I place a magnet north and south pole like this. Okay, north and south. So now, here got magnet. North and south. So surrounding this magnet, there is a magnetic field, which is what? Spread outward, right? Outward. But we can't see the magnetic field. Okay, spread outward. Okay, it is spreading outward. Okay, so there will be magnetic fields like this. Away from north towards the south. So now, let's say this is a magnet. Okay, this is a magnet. When the magnet is being pushed into the solenoid, that means what? Here got magnetic field, right? There's a magnetic field. Okay, magnet. So at the end over here, there's a magnetic field. It's what? Spreading outward. Okay, so magnetic field, when here's a solenoid. Once you push the magnet in, what happens? It will cut the magnetic flux. Once you push the magnet in, the magnetic field over here will be cut by the solenoid. Here, solenoid. Once I push the magnet in, what happened? Surrounding it got magnetic field, right? So what happened? When you push, the conductor over here will cut the magnetic fields that produced. Okay? So when it's cut the magnetic fields or magnetic flux, what happened? Current induced. Current induced. So the induced current flow in which direction? Just now, in a straight wire, move up or move down, induced current we identify using Fleming's right hand rule. But now, current induced in a straight wire, how you're going to identify? We have to apply a rule or law. So that one we say what is this? What is?
Lens.
Lens means what? This is a lens, right? This is a lens, yeah? Lens. But here, not lens, that is L-E-N-Z. Okay, we have to write in the proper way, with the correct spelling. Don't write L-E-N as here. So, lens followed by apostrophe S. Lens law. So, Fleming's right-hand rule is used to identify the direction of induced current in a straight wire. But in a solenoid, follow what is stated by Lenz's law. Lenz's law specific to identify the direction of the induced current in a solenoid. So what is stated? What is stated? So Lenz's law states that current induced in a solenoid, current induced in a solenoid always flow in the direction, okay, in the direction oppose the motion that induce it. Looks like a bit confusing, eh? A bit confusing. I repeat, Lenz's law states that current induced in a solenoid always flow in the direction oppose the motion that induce it. Oppose. In BM, we say like this. Hukum Lenz menyatakan bahawa arus teraruh dalam satu solenoid sentiasa mengalir dalam arah yang menentang gerakan yang menghasilkannya. means the movement of the magnet in to the solenoid. Remember, the movement of the magnet into the solenoid will cause the magnetic field being cut. Okay, so the movement of the magnet must be opposed. Must be opposed. Suryadev, if you can send later to the group here. Let's listen first, okay? So the movement of the magnet in to the solenoid, what happens? It will induce current. It will induce current. That means the induced current, when the current flow, okay, last time we already studied this. There is a solenoid, soft iron core. Okay, soft iron core. Let's say here we supply with the current flow. What happens here become north, over here becomes south, right? When current flow, one of the end become north pole, one more end become south pole. Okay, but here the movement of the magnet into the solenoid will induce current or produce current. So the current that induce flow, what happens? It will produce north and also south pole at the end of this core. Okay, it will produce poles of magnet. So current induced, right? Current induced. Why current induced? Magnet move in. Magnet move in, it induce the current. Okay, magnet move in, it is induced current. Okay, it is induced the current. So when then the induced current always opposed. So please underline the word opposed. Means magnet, you want to move towards the solenoid. So now, what pole is entering? North pole is entering. So what happens when north pole is entering? Current induced. Yes, current induced. But the induced current always opposed. To oppose the movement, to against the movement. Here, the current induced must produce north pole so that it can oppose. Movement of magnet in induced current. But the induced current always flow in the direction opposite to oppose the movement of the magnet, current induced must produce north pole over here so that it can against or oppose. So now if you're not over here south, let's use a right hand grip rule. Not curl the fingers, not curl the fingers. It is what? Upward, current flowing upward. Okay, current flowing is upward. Okay, now the next one is okay. So when the current is flowing upward, goes upward and then come to here downward. So what happens? The pointer of the galvanometer will deflect to the right. Deflect to the right. Okay. Now let's say the magnet is inside. Okay, the magnet is inside. South. Here is north. Okay, north is inside. Coil okay, solenoid over here is at rest. But now you are going to pull out the magnet. Okay, here got solenoid. The magnet is what? Inside. There is a magnetic field, right? There is a magnetic field. So once you pull out the magnet, here's solenoid. Once you pull out, what happens? The magnetic field also what? Also being cut. It is cutting the magnetic field. So now when you move out, you see over here, what pole is it moving out of the solenoid? North pole. Then what happened? Current induced, reduced. So current induced always flow in the direction opposed. Just now one to goes in, repel. But now You want to pull, the magnet want to leave, it must attract. Okay, it must attract. Suryadev, you can forward any messages to the group regarding physics later. Please listen first, yeah? Okay, so what pole that leaving the solenoid? Not. So if want to leave, it must oppose. So it must attract. So the current that flow in the solenoid, what happens? It will produce south pole over here and over here north. So that south pole, when the north pole want to leave, it will attract. It will attract. So it always what? Always oppose the motion. Okay, always what? Oppose the motion. So now here north, over here south. Let's check north, south, curl the fingers, current in front, downward. In front, downward. So current is downward. Downward. So the pointer of the galvanometer deflect to the left. Okay, it is deflect to the left. Okay. Okay, now I'm going to show you activity so that you can get idea. So remember, the Lenz's law is used specific to identify the direction of the induced current. Yeah? Okay. No need to give any comment in the group right now. Yeah, listen first. Yeah. Okay. Look at here. I place the galvanometer facing to you. No need to delete anything in the group. Leave it so that we can share the good informations. Okay. No need to delete. It's good actually if you are sharing the something that related to physics. Okay, good. Okay. Now here I connect two wires to the galvanometer, centered zero galvanometer. Okay, can see. Okay, here got a solenoid, and one of the terminal I connect to here. One more terminal over here. Must grip tightly. Okay. Now I want all of you to look at the pointer of the galvanometer. Can see or not? Pointer of the galvanometer. Or you want me to lower a bit? Wait.
Cancer.
Cancer, it's okay.
Can I?
Yeah, cancer, it's perfect.
Okay. Okay, look at the pointer, yeah? Pointer of the galvanometer. Okay. And here is a solenoid. and then you see the pointer here. You look at the pointer of the galvanometer. Now what I'm going to do, what pole? North pole. North pole is going to be pushed in. Oh, got problem. Got problem. Hey, it's not working. The string is working. Hey. Got problem. Hey. Oh, it is not working. Wait. This S3 is working. Wait for a while. Don't let the class. Another law I will repeat next week. Okay, but still we need to practice to draw the draw the current and also identify the poles. Yeah. Okay. It is not working. S3 is working. You don't have any luck today. Okay. If you want to wait, can wait for a while. I try and see the another wire. Oh, it is not working. Okay, good. It's working. Okay, what is this? Surya, there is any video to repair all meters? No need. Listen first. Okay, here is a centered zero galvanometer, and then over here is what? Magnet. And then here is north pole, yeah, going to move in. You see the deflection, yeah? 1, 2, 3. Where is it is deflect? Right or left? Right or left?
Right.
Right. I repeat, if I move the magnet in, it is deflecting to the
Right.
right. Okay, now the magnet is inside. If I pull out the magnet, pull out, where?
Left.
Left. Okay, it is deflecting to the left. I push in to the right, pull out to the left. Correct? So, again, push, not pull in to the right, pull out to the left. So, right, left. Okay, look at here. I'm turning the magnet. What pole is going to enter? South pole. So, just now, right, south pole is going to in. What happened? I repeat, in. It is deflecting to the left.
Left.
If I pull out, to the right. Left, right. If I turn, north, right, left. What happened? So they mean very simple. If the north pole move in front over here, current induced, yes, in front must produce what? North pole. So that current flow in the direction opposed to motion. So in is deflect to right. Okay, when the north pole is moving out, north pole leaving, current induced, yes, but it must oppose. So if the north pole want to leave, here must be a south. South, so that it can oppose the motion. Okay, so now if the magnet is moved in to the right, pull out to the left. Okay, but now magnet is rest. Okay, magnet is at rest. If I move the solenoid in, is it got current? Got or not?
Got,
Got or
sir.
not? Yes, got. That means any one magnet or solenoid must move. Then what? Current induced. Okay, so now look at this. If the magnet is inside, is it current induced? No, because it is not cutting the magnetic flux. No current induced. If I move both together, is it got deflection? No, no current induced. No current induced. If I move both away, got not? Got right? Got current induced. That means there must be relative motion. We say perbezaan gerakan. Okay, now if I move the magnet in and out slowly, is it current induced? Yes, current induced. Can see the deflection? Okay, you see that? If I move the magnet in and out, current induced? Yes, small current induced. But if I move faster, what happened? Deflection greater means what? Means current induced what? Greater current induced. So the magnitude of current induced, it refers to another law. Okay, another law. Okay, yesterday I already explained about the Faraday wave, and also I already asked my students to draw a few more diagrams to show to understand the Lenz's law. Okay, next Saturday, please remind me. I will try to repeat again the Lenz's law and also Faraday's law. After that, we go through the experiment. Then we are going to go through the generators. Yeah, so you have to print out the notes I already sent you 2 weeks before. The DC motor over there also we got a generators. Okay, so I think I want to stop over here. Now it's already 11:10. So see you on next week. I will repeat this next week and then straight we go to the diagram. Yeah, can or not? Okay. Okay, that's all for
Thank
today.
you, sir. Thank you, sir.
Yes.
Thank you, sir.
Thank
Sir?
you,
sir. Thank you,
yes.
sir.
Okay, I'm waiting. Yes. Tell me.
Sir, just now when you were explaining about the solenoid, you were showing about the magnet and the solenoid.
Yeah.
Wait, you mentioned something called relative motion. What is that, sir?
Relative motion, that means there must be a difference in the motion.
Oh.
Difference in the motion. That means, let's say, is it got any difference in the motion? No.
No.
If move in, yes, that's a difference. If you pull out, yes, that's a difference. That means there must be in BA we say laju relative. That means there's a difference in the reading. Okay?
Oh, okay.
It's in one side out. Or solenoid magnet rest, solenoid move in or move out. That means must be difference in the speed. There must be difference in the motion. I mean, there must be a cutting of magnetic flux. Okay.
Thank you, sir.
Welcome.
Sir.
Can't hear.
Sir, I have a
Yeah.
question. Just now when sir showed bar magnet when he entered the solenoid, so I'm a bit confused with the magnetic.
Wait.
I'm a bit confused with the magnetic pole. Like when it enters, the front of the solenoid becomes not right, but when you pull out the magnet, the front of the solenoid becomes.
Okay. I got your point. Very simple. You just follow what is stated by Lenz's law. What is stated by Lenz's law? Lenz's law states what? Current induced always flow in the direction opposed. So if let's say if you push the magnet in, move the magnet, there's a magnetic field, will be cut. Current induced. So if the magnet want to go in, check first what pole is entering, current induced must oppose. It's very simple. Want to go in, repel. If let's say you want to pull out, it will attract. Simple. You remember this way. Actually, we straight away apply Lenz's law. Lenz's law states that current induced always flow in the direction opposed the motion. So 1, 2 goes in, check first what pole. So here it will produce the same pole so that it can against. If you want to pull out, see what pole leaving, here produce unlike poles so that it can attract. Okay, so the rules is a specific rule. Just want to identify easily the direction of the induced current in solenoid. Okay, so very simple. Now one more is, let's say the south pole. South pole going in. Here south pole. Simple. Then you can check the current. If the south pole leaving, it must attract. So the keyword is what? Oppose. 1, 2 goes in, repel. 1, 2 goes out, attract. You just use this concept and you already. Anyhow, next week I'll repeat this again. We will draw a few more diagrams. Then still we'll continue with the Faraday's law and also experiment. Okay?
Okay, sir.
Okay, then I will repeat again. Don't worry.
Okay, sir.
Okay. Okay.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir. Bye.
Bye-bye.
Thank you, sir.